Hello everyone, it's Friday, which means it's time for another studio review video. This time we are reviewing Studio 3, which has you creating something called the Sieve of Eratosthenes. It's a very hard to pronounce way of finding prime numbers. So before we hop into the code, I do want to kind of set the background for what we're going to try to do. I think it's very important to understand the process. We have a whole lot of stuff up in the front of the studio. We asked you to work through some stuff on paper just to make sure you understand the process of what you're being asked to do before you actually start to write some code. This is, I think, very important, but often overlooked. Students can sometimes just sit down at the computer and start typing out code until something sticks, something starts to work. But with a little bit of thought, with a little bit of preparation, and even working some stuff out on a whiteboard or paper and pencil, writing out the code can actually become a much smoother process. So let's talk about this sieve of Eratosthenes. We linked you to the Wikipedia page, and I hope you took a look at this. The way that it works is we're going to first assume that all numbers are, we're going to assume that all numbers are prime. We're going to start by making the very incorrect assumption that all numbers are prime, and then we'll start by marking numbers not prime. So by this illustration here, you can see we're going to start with the number 2, and then we're going to mark every second number as not prime until we get to the end of whatever range that we're looking for. In this example, they go up to 120. Once we get done with the multiples of 2, we'll then mark all the multiples of 3 as not prime. We'll mark all the multiples of, so we can actually skip 4, right? But we could also do 4 if we wanted to. We can mark all the multiples of 4 as not prime, all the multiples of 5, all the multiples of 6. By the time we get done with this, right, by the time we've marked all of the multiples as not prime, then what remains are the prime numbers. So anything that has not been marked off as being unprime must then be a prime value. And so if you kind of keep watching this example, where it's actually kind of nearing the end here, right, it's going to start picking out the prime numbers now. Anything that has not been marked as unprime remains as a prime number. This structure here looks a bit like the topic that we've been talking about this week, although I wish they would have maybe illustrated it a bit more closely to our mental picture of an array. This looks awfully like a two-dimensional array, but it's really not. It's a one-dimensional array that goes from 2 to 120. And so our first step is going to be asking the user how many prime numbers, up to what value of n they want. So in this case, n is 120. We find all of the prime numbers less than n, or including n as well. So yeah, that's going to be our first step. We'll then create the array, and then we'll start this process of marking off multiples, starting with 2. We'll mark all the multiples of 2 as not prime, then multiples of 3. Let's see how we can start to piece this together in code. First thing we're going to need is a scanner, since we do need to prompt our user for a value for n. So I'll go ahead and get that set up. Again, if you don't know how to do this, still, that's not a problem. I have to be honest with you. I still was Googling how to use the scanner, even up to a couple years ago, and I've been doing this for a long time. So there's really no shame in having to go back and look this up either on Google or in a past, studio that you've done if you need a little refresher on how to grab this code, on how to make this code work for the scanner. We're going to make a variable called n. And this is the value, remember, that we are going to find all of the primes less than, and we can do equal to n as well. So actually, before I do this, though, I want to make a prompt. Let's say, please enter a value for n. There we go. That'll do the trick. And now we can make our integer n and grab the next int from the scanner. Our next task is going to be to create an array, and we have an option here. Going back to this diagram, we can see that, okay, this array kind of looks like it might be an array of integers. I actually see that there's numbers inside of each one of these boxes. However, I would actually like to think about this a little bit differently. I think there's another choice that we could make here. What if these numbers, instead of representing the values that the array contains, what if we think about these numbers as the index into an array, and the value then is whether the number is prime or not, whether the index is prime or not. So what that means is if I want to look up a value to see whether it's prime or not, I run this process, and at the end I just say, all right, 55, is that prime or not? Either it's going to say true or false. True meaning it's prime, and false meaning it's not prime, which is case for 55, right? If I want to look up 67, I just go to that spot in my array. It's either going to say true or false, right? In this case, 67, I believe, is prime, so it would say true once we're done with this process. So let's go ahead and think about how that's going to affect our array. A lot of students like to make their array as an integer array. You can do it this way. I don't want to make it sound like you can't. You actually can, but I really think a Boolean array is a better fit. So we're going to use the index to represent, a value, a number, and then what the array contains at that index will be either true or false. True means that the index is a prime number. False means that the index is not a prime number. We have to create this array. So if I say, new Boolean array, we have to fill in a number here, which is how big we want this array to be. If I wish to include n, I actually have to put n plus 1 here, right? Remember that arrays start from 0. So if I want to make sure that the index includes n, I have to add 1 to it, because otherwise it would be, the last index in this array would be n minus 1. So there's a little tweak there that I've made just to make sure that we're including n. If you don't want to include n as part of your prime checks, that's fine. You actually have that option. You can leave that part off. It doesn't make a huge difference. And now we have the actual work of finding primes themselves. So we can actually start with 2, and we want to check all the multiples of 2, and then we want to check all the multiples of 3, and then we want to check all the multiples of, let's say, 4. There's a pattern there, right? So I can see the counting. I can see the counting going upwards. 2, then 3, then 4. When do we stop? I can stop when I've hit n. That is one possible stopping point. We could actually stop sooner than that, though. We could stop when I've gotten up to half of the values, because if I've already checked the multiples up to n over 2, there's no possible way I'm going to find any multiples bigger than that, right, in this data set. And actually, mathematically, it's been proven that we can stop even earlier than that. But let's just keep it simple for now. I'm going to make a loop, and this loop is going to represent which multiple we are currently figuring out. So I'm going to say I is going to start at not 0. I know 0 is a tempting choice, right, because our array starts at a 0. But I'm going to say, for I is equal to 2. 2 is the first value that I wish to check the multiples of. I is less than, we'll say I is less than, I'll just say, let's see, n divided by 2, right? That's when we're going to stop. And then we'll do I++ for the update. Now at this point in time, we start to want to check to see if we want to start checking to see if we have some prime numbers. And this is actually one of the situations where I see students kind of take a wrong turn. They might do something like, if I modulus 2 is equal to, is not equal to 0, right? That means that, maybe it's not going to be a prime number, and then they'll keep doing, or actually I should say this the opposite way. If I mod 2 is equal to 0, then we know it's not prime, right? Else if I modulus 3 is equal to 0, then we know it's not prime. I can understand why modulus would seem like it's an appropriate tool to use here, and if, there are other ways of searching for prime values that perhaps would lean on this modulus operator, but this problem actually I don't believe needs the modulus operator. In fact, this approach, while somewhat intuitive, will not work. And to explain why, consider that I can check some values like this, 2, 3, 5, 7, but eventually if n is large enough, right, it's not going to work anymore. So this, I can check 2, 3, 5, and 7, and that might help me find all the primes under 100. But then if I say, give me the primes under 10,000, then I need to add, 11 onto that list. Probably need to add 13 onto that list as well. And then, who knows how many else ifs I'm going to need after that point. And then no matter, how many primes, how many else ifs you add, I can always pick a number for n that is even bigger that is going to cause this method to fail. So this method is simply just not foolproof for all values of n. And that really is a problem for us. Having programs that only work under certain conditions is generally considered not a good thing. We much prefer a program that will work for all values of n, not just certain values of n. So this isn't the right approach. Instead, I want to think of I not as the value that we're checking to see if it's prime or not, but again, we're using I to compute multiples. So I want to use I to compute all the multiples of 2. I want something to go 2, 4, 6, 8, etc., 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 and I want to mark all of those as not prime. And really, that sounds like another loop to me. This sounds like another loop. And this loop is going to be a little bit tricky. I'm going to make the loop variable for this one called j. And I want for j to start at the first multiple of I. We can actually just have it start at I, right? J is less than or equal to n, since n is included. And then j is not going to go plus plus. We want j to represent multiples of multiples of I. So j is equal to, what do I need to say here? J is equal to j plus I. So the first time through this loop, j will be 2. The next time through the loop, I'll add I to it, which makes it 4. The next time through the loop, I'll add I to it again, which makes it 6, and so on and so on and so on. All right. So j is going to compute the multiples for us, and we now have the very simple job of just marking those multiples as false. We need to access our array to do this, and it's going to be fairly simple. Primes at j, which is our multiple, equals false. Now I want to pause here for a second. It seems like I wrote this out fairly quickly. I mean, this is actually pretty good. I think you'd be surprised at how good even this simple amount of code is at detecting primes. But, I haven't actually shown you that it works yet or how it works. So let's come down here and just to kind of wrap things up so we can kind of take a look and see if this is actually working or not. I'm going to put a loop down here after this to print the primes. So the idea is that once I get through these 4 loops, it's going to go and mark all of the multiples for 2 and then 3, 5, etc. Once it gets done, then we're going to come down here and just print out that list. And to do this, I'm going to use a for each loop. It's a little bit different than... Oh, actually, no, I'm not going to use a for each loop. I don't think I can use a for each loop for this because the index matters. The index is important. So I'm going to write a loop that actually looks very much like this one. It's going to look a little bit different. I'll just use the length of the array here. If the value in my primes array at position I is true, then print it out. If it's false, this will get skipped. We won't print it out. It won't be shown to us as a prime. Let's test our code. I think there might be some problems with it, but I've written a little bit of code. I think, maybe I moved in the right direction. Let's test it out. Let's see if it works and fix any bugs, fix any issues that might exist. I'll just keep it simple for now. All the values up to 100 and nothing printed out. My program is done. So that's a little bit confusing, but let's try and, work our way backwards and think about what this means. That means that when it got down here, all of the values in the array were false. Didn't find a single true value to print out. And that kind of brings me to this question up here of like, what is in this array to start with? Do I know what's in this array to start with? There's a few different ways that we could actually check this to see. We could, of course, print some values out, or we can use the debugger, and that's what I'm going to do. I'm going to set a breakpoint right here on line number 12. Once I enter a value for n, it'll pause at the breakpoint for me on line 12, and I can take a look at this array after it gets created to see what it looks like. And if I expand the values, you can see, oh, okay, when I create this array for the first time, all of the values are false. So an empty Boolean array contains all false values. This is a problem for us, right? Our algorithm, our approach to finding primes says we're going to assume that everything is prime to start with. So we want all these values to be true so that these loops can mark the unprimed values as false. But that's okay. We can fix this problem. This is a solvable problem. We just need to make sure that it's all these values start as true. So let's go ahead and do that by writing another loop. Loops and arrays go very well together. As you can see, this loop is going to be very simple, very straightforward. We'll just write a loop to visit each element in my primes array. Actually, I could have started this at 2 since we're not worrying about 0 and 1 for the purposes of this exercise. And we'll simply set all of the values equal to true in the array to start with. That should take care of that little problem for us. Let's go ahead and run this code again and see if we get some primes back out this time. I'm not going to do the debugger. I'm just going to run it normally and see. Okay. Clearly there's still some kind of a problem here. I see these numbers, I believe, actually are prime, but for some reason, I'm not seeing anything less than 53. That seems like that could be potentially a mistake. I actually think there is a mistake, right? And this is a tricky one. Let's run it through the debugger and see if we can't figure out what's happening here. I'm going to set that breakpoint on line 16. I'm going to enter in a number for 100. This is going to give us, oh, I have my breakpoint set from before. I didn't even realize. Okay, if I hit the continue button or the resume button, it's going to jump me down to my next breakpoint. And now we can see our primes array is set to be all trues except for 0 and 1, which we're ignoring. So, right, so everything is true. And now we're at the point of the code where it should mark, the non-primes as false. So let's step through and see if we can't figure out what's going wrong, why it's not picking up those early primes. We're starting out at I is equal to 2. We can see that over here in our variables window. We then start j is equal to 2, and then we immediately say primes at j is equal to false. Well, wait a second, that's not true. J is 2. 2 is prime. That is, in fact, a prime value. So we've actually started computing multiples a little bit too early. In other words, j is too small at the beginning of this loop. We need to start j at not I, but I plus I. We need to start it at 2i, 2 times I. It's going to make a difference. In fact, I want to show that to you again in the debugger. I'll enter my value for n. And here we go. This time around, no, I don't want to look at that array right now. Here we go. I is equal to 2. J is now not equal to 2, but 4, right? The first multiple. 2 times that. So it's going to mark 4 as not prime, which is correct. And then J is going to go up. It's going to mark 6 as not prime, which is correct. It's going to mark 8, right? You can see, I'm going to click on this very fast, see if I can get through all these. On the right-hand side, you can see all of the even numbers are currently being marked as not prime. So let's go ahead. Almost to the end now. I'm going to go through one more multiple. 800. All right. We've finished all the multiples of 2. I is going to bump itself up. It's now 3. We're going to compute all the multiples of 3. 6 is not prime. 9 is not prime, etc. These are all not prime values. 3 itself is, though. And 3, thankfully, remains untouched. So that's good. That works out. Okay, now we're checking I is equal to 4. Now this one, while it's not necessarily wrong to do this, pay attention to the fact that by computing the multiples of 4, they're also multiples of 2. So this is actually kind of redundant to do this. While not strictly incorrect from a mathematical standpoint, it's not necessary either. It's extra work that is not necessary for us to do. And this could make a difference. In fact, the last part of this studio, I want to spend some time talking about how we can make this run a little bit better, a little bit more efficiently. Let me see if I can actually push this to its limit. Well, let's check it and make sure it works first, and then we'll talk about optimization and efficiency. First, let's see if we fixed the problem and it can properly print all of the primes less than 100. Here we go, 2, 3, 5, 7. Those are primes, all right. Those are all the prime numbers less than 100. Beautiful. If you got this far in Studio, I would be very happy with that. I would say this is a great place to end up with, to end up on this Studio. But we can make it even better. And to illustrate why we might want to do that, let's, for a second, choose a bigger value for n. Let's start to see if we can push this to its limit. If I say 10,000, okay, that one actually still went pretty fast. Let's keep going. Let's try 1,000,000. Ooh, still not bad. Let's try 1,000,000,000. That's 1,000,000,000. I want to find all the primes less than 1,000,000,000. And now you can see, okay, the computer has taken a little bit of time to figure this one out. But as it's doing this, I want to reiterate that it's doing extra work, right? It's computing all those multiples of 4 that it does not have to compute. Those are not necessary. That's already been covered by the multiples of 2. And that's true for other higher multiples as well, as you can possibly imagine. So how can we avoid that? How can we avoid that? Consider, I mean, the Wikipedia page, I think, mentions this as well. We only need to compute the multiples of the prime numbers themselves. So I actually only need to compute the multiples of 2, 3, 5, 7, 11, etc., etc., etc. I don't need to do all of that redundant extra computation for those in-between values. So how do we know if we need to compute the multiple of a value or not? We need to know if that value is prime. Well, wait a second. We have a way to check to see if something is prime or not. We're making an array for that specific purpose. So this is stuck. I mean, I think it's actually working. I think it's actually trying to do what I asked it to, but it's taking a very long time. I want to see if I can fix this and make it not take such a long time. I'm just going to come in here. I'm going to put in an if statement that says if primes at I is equal to true. And the reason, again, why I'm doing this is so that this loop here only executes for prime numbers. I'm only computing the multiples of 2, 3, 5, etc. I'll leave a little comment to show that that's the case. Let's try and enter 1,000,000,000 and see if we've made a difference. See if it's actually able to complete in a reasonable amount of time, since we've eliminated that redundant work. Last time, I mean, I sat here for, I don't know, a good 30 seconds to a minute, didn't even finish. So if this one finishes in any sort of reasonable time, I would consider that to be a win. Although you can see it's still, oh, it finished. It finished. It actually finished and found all of the primes less than 1,000,000,000. We're seeing those being printed out right now. I'm not actually going to sit here and verify if all of these primes are correct. That would take quite some time. And you can actually see that just to print them out takes quite some time. But let's go ahead and see if we can't make one more slight optimization to this. Here we're computing all of the multiples from 2 up to n over 2. And we actually don't even need to go that high. I'm not going to do the mathematical proof for you. This really isn't that kind of a class. But we can stop earlier. We can stop at the square root of n. So instead of going up to n over 2, we can stop at the square root of n instead, which is less. That's less than n over 2. So this should save us even more time. There's even fewer multiples that we have to compute now. Let's run this again for 1,000,000,000 and see if it's actually making a difference. So, you know, the first time took a really long time. Second time it still took a little while, but it did finish. Let's see, this time it should start any second now. Where are you? Oh, there it goes. I'm not going to sugarcoat it. A little hard to tell in that particular example how much this optimization saved us. Seems plausible that it did save us at least a little bit of time. Definitely, I think, was you know, easier to see the time savings when we included this optimization. And you know, both of them put together should give us a pretty efficient way of finding prime values. Printing these numbers out, by the way, you can see is also quite time consuming. So you know, just taking out the print statements will speed this up quite a lot. Which most of the time we don't necessarily need to see the prime numbers, right? We just want to have them. We want to use them. They have lots of very cool purposes in mathematics as well as computer security. It turns out prime numbers are extremely important to cryptography. So that's one reason why we as computer scientists really, really, really like to think about prime numbers. But yeah, I think that's going to wrap it up for this studio. This is a fun little exercise. I hope you were able to come up with a pretty decent solution, and I hope you were able to understand this walkthrough as well. Your assignment this week is going to focus on arrays. Be sure to check the rubric. Make sure you know what's going on. I've been very happy with how things have been going. It's been a very smooth semester so far. Hope it keeps up, and I will see you in class on Monday. Remember, Monday we'll be doing our first review for exam 1, which is coming up on Thursday next week. So 1 week from Thursday, a little bit less than a week from when this video gets posted, will be our first exam, and we're going to be reviewing for that in class on Monday. All right, everybody, I think that's going to do it for this week's studio review. I hope you all have a great weekend. I'll see you in class next week.